Hello and welcome back to the Biochemistry for Health Sciences channel. In today's video, we'll talk about how we determine the velocity of enzyme-catalyzed reactions. In previous videos, we discussed how enzymes use various strategies to increase the velocity or the rate of chemical reactions. So in enzyme studies, we come across this term velocity very often in equations as well as in various graphs that we shall discuss in the near future. Compared to other types of proteins such as transport proteins or DNA binding proteins, or cell signaling proteins, enzyme function is probably one of the easiest to study, and that's because enzymes change or increase the velocity of chemical reactions, and measuring the velocity of chemical reactions is quite easy to do. So consider this reaction where the substrates or the reactants A plus B react to give you the products C plus D. The velocity or the rate of this reaction is basically the amount, and the amount could be in units such as micromoles or nanomoles, of the substrate or reactant, that is either A or B, that is consumed, or the product C or D that is formed per minute under specified conditions. And the two very important conditions we need to specify for enzyme-catalyzed reactions are pH and temperature. So for example, in this graph on the left-hand side, we are following the amount of product C or product D with time. And so you can see in this example, the velocity of the reaction, which is basically the slope of this line, can easily be determined. You can see that the amount of product increased by 10 micromoles in 2 minutes. So 10 micromoles divided by 2 minutes will give us 5 micromole per minute. So basically the velocity of this reaction is 5 micromoles per minute. Now in the graph shown on the right-hand side, we are following the amount of substrate A or B that is consumed with time. So in this case, we can determine once again the velocity by determining the slope of the line. So for example, in this case, we have the amount of substrate going down from 40 to 20 micromoles, so 40 minus 20, and this is happening in 2 minutes. So 40 minus 20 is 20 micromoles, and that change is happening in 2 minutes. That will give us a slope of 10 micromole per minute. So in this example, the velocity of the reaction is 10 micromoles substrate consumed per minute. And in this example, the velocity of the reaction is 5 micromoles product formed per minute. So velocity could be determined either by monitoring the substrate or the products. One of the most common and easiest way to follow chemical reactions is if one of the reactants or the products absorb either ultraviolet light or visible light. So for example, let's say this product D here has a strong absorbance of visible light at 405 nanometers. In that case, we can follow this reaction by following the absorbance at 405 nanometers with time. Measuring absorbance can easily be done by using quite an inexpensive instrument that's readily available in most labs, and this instrument is called a UV visible spectrophotometer. The ultraviolet light has a wavelength around 200 to 350 nanometers, while visible light has a wavelength range from around 350 to 800 nanometers. As we shall see later, this absorbance can be converted into the amount. And this can be done by using the Beer-Lambert law, using this equation that we shall look at in a few minutes. So basically what we do in such a experiment is we add our reactants A plus B, we add the buffer of the appropriate pH, set the temperature, and we can run this either with enzyme or without enzyme as a control. And we follow the change in absorbance with time. There are two common ways of doing this. One is called the kinetic assay and the other is called the endpoint assay. In kinetic assay, we continuously monitor the change in absorbance versus time. While in endpoint assay, we actually destroy the enzyme after a fixed amount of incubation time, and then we measure the change in absorbance. This destroying the enzyme can very easily be done by either adding a very strong acid or a base, because most enzymes would not survive extremes of pH. So let's look at a few examples. Let's look at this enzyme lactate dehydrogenase that we'll talk about under metabolism. We add to the test tube the reactants, some lactate salt, so in this case lithium lactate, and the other reactant NAD. And then of course we add an appropriate buffer, and then we set the temperature. The two most common temperatures that are often used is 25 Celsius or 37 Celsius. Now, out of all these reactants and products, only NADH has a strong absorbance at 340 nanometers. So we could follow this reaction by monitoring the absorbance at 340 nanometers with time. So you can see in the presence of enzyme, the reaction is much faster compared to without enzyme. Here's another example, and this is for alkaline phosphatase. So once again, we take a tube, we put in the substrate, which is para-nitrophenol phosphate. Water is in the buffer, so we have a buffer to maintain the pH, and then we set the temperature at 25 or 37 Celsius. We follow this reaction by following this product here, para-nitrophenol, which shows a strong absorbance in the visible range of 405 nanometers. So we follow the absorbance at 405 nanometers with time, and once again, in the presence of the enzyme, you see a much better slope, much higher slope, compared to without enzyme. So once we have this absorbance change with time, we can now use the Beer-Lambert law to calculate the concentration or the amount, in this case of para-nitrophenolate that is formed. So here's an actual example. Let's say the slope of the line that we obtain, the delta A per minute, change in absorbance per minute, came out to be 0.4. So this is 0.4 change, and this happened in 2 minutes. So 0.4 divided by 2. So our slope is 0.2 absorbance unit change per minute. Now we use the Beer-Lambert's law and rearrange it to find the concentration or amount of para-nitrophenol, the product. And that would be the absorbance divided by this E here, that's called the molar extinction coefficient, and L here is called the pad length of the cuvette. This L here is called the pad length, and is basically the distance the light travels in the tube. And this distance is usually 1 centimeter for most of these tubes that are called cuvettes. For para-nitrophenol, which is the product we are monitoring, the molar extinction coefficient that can be obtained readily from literature is 18.8 per millimolar per centimeter. So using this rearranged equation, we can calculate the concentration of para-nitrophenol per minute, and that is basically your delta A per minute divided by the molar extinction coefficient divided by the pad length of the cuvette. So if we plug in these numbers, delta A per minute is 0.2 per minute, the molar extinction coefficient is 18.8, and the pad length is 1 centimeter, we will get, in this case, a PNP form per minute of 0.01 millimolar per minute, which is equal to 10 micromolar per minute. And that's basically 10 micromoles per liter, that's your 10 micromolar, form per minute, which is the same as saying 10 nanomoles per milliliter, that is form per minute. So in this experiment, for example, we took 5 microliter of the enzyme and added it to the rest of the solutions, that is the buffers and the substrates and so on. Let's say the rest of it came out to be 500 microliters. So we can calculate the actual amount that is formed in the tube, the actual amount of para-nitrophenol formed in the tube. So we have 10 nanomoles formed per milliliter, so 0.505 milliliters, and this 505 basically came from 500 plus 5, that's 505 microliters, which is the same as 0.505 milliliters. So multiplying this by 10, that gives us 5.05 nanomoles of product para-nitrophenol is formed in the tube per minute. So the velocity of this reaction here in terms of amount of product is 5.05 nanomoles per minute. So that's how we find the velocity or the rate of a chemical reaction. Now that we know how to determine the velocity of a reaction, we shall use this in the next video to study the properties of enzymes in a field called enzyme kinetics. Until next time, have a good day. Goodbye.